So, let us now work out some problems based on divided differences. Let P be the polynomial, let P be the polynomial of degree at most n that interpolates a function f at a set of n plus 1 distinct points. Say x0, x1, etc., xn. If t is different from these xi for I is equal to 0, 1, 2, 3, etc., n, then show that f of t minus p of t. So, what is it? What is f of t minus p of t? P of t interpolates the function at a set of discrete points which are distinct, namely x0, x1, etc., xn, and t is any point in that interval which is different from these xi. So, f of t minus p of t gives you error in the approximation of f of t by p of t at the point t in that interval. The result says this error is f of x0, x1, etc., xn t. So, there are n plus 1 points and there is an additional point n plus 2 points. So, it is the n plus 1th order divided difference multiplied by the product of the factors j is equal to 0 to n t minus xj, where by j equal to 0 to n t minus xj we mean t minus x0 into t minus x1, etc., up to t minus xn. So, the problem essentially gives us an expression for error in interpolation in terms of the divided differences. So, let us try to work out the details. So, let Q be the polynomial or interpolating polynomial of degree at most n plus 1 that interpolates the function at, it is a polynomial of degree at most n plus 1. So, that interpolates the function at a set of n plus 2 discrete points. So, at say x0, x1, etc., xn, we have n plus 1 of them and t. So, we have n plus 2 such points. And so, can we write down what this polynomial q when we know the polynomial p? Yes, that is the advantage of divided difference interpolation polynomial that we had seen earlier. So, I can write down q at any x will be equal to p of x polynomial of degree n plus the additional term. The additional term will be that a n plus 1 into product of certain factors. That a n plus 1 will be the divided difference f of x0, x1, x2, etc., xn t multiplied by the factor x minus x0, x minus x1, etc., up to x minus xn. So, how many such factors are there? Starting from x minus x0 up to x minus xn, there are n plus 1 factors. So, this is a polynomial of degree n plus 1, its coefficient is this n plus 1th order divided difference, and it is added to a polynomial of degree at most n. So, that will be the polynomial q of x. So, therefore, what And what do we know about q at t? So, q at t is f at t. Why? How have we constructed q? Q is the interpolating polynomial of degree at most n plus 1 that interpolates the function at x0, x1, etc., xn and t. So, q at t will be f at t. So, I evaluate this at t. So, I have f of t will be p of t plus f of x0, x1, etc., xn t multiplied by t minus x0 into t minus x1, etc., up to t minus xn. Therefore, we have f of t minus p of t to be equal to f of x0, x1, etc., xn t into product, say j is equal to 0 to n t minus xj, and that is what we have to show here. So, this gives you the error in interpolation in terms of the divided differences. Okay. So, let us now continue with another problem which says if f is n times differentiable, if f is n times differentiable, say on the interval a b, and if x0, x1, etc., xn are distinct points, they are distinct points in the interval a b, then there exists a psi in the open interval a b such that f of x0, x1, etc., xn, the nth order divided difference is 1 by n factorial into the nth derivative of f at psi. The nth order divided difference is the nth derivative at psi by n factorial. And you now look at the previous problem and this problem. If you use this information in this result, right, the nth order divided difference is 1 by n factorial into nth derivative at psi. So, I have a n plus 1th order divided difference here. So, if I prove this problem, then I can express this as the n plus 1th order derivative of f at psi by n plus 1 factorial, right, provided f is n plus 1 times differentiable in that interval. So, if I substitute in terms of this result, then I essentially get the result which we have already computed for error in interpolation, namely f of t minus p of t is n plus 1th derivative at psi by n plus 1 factorial into the product of certain factors which we had denoted earlier by pi n plus 1 of x. So, let us work out the details of the proof of this problem. So, what do we have to show? F is n times differentiable on AB, and there are n plus 1 distinct points in AB. Then there exists a psi in AB such that the nth order divided difference is this given in terms of the nth derivative of f at some psi which belongs to this interval AB by n factorial. So, let us take P be the polynomial, of course the interpolating polynomial of degree at most say n minus 1 that interpolates the function f. It interpolates f at how many points? P is a polynomial of degree at most n minus 1. So, there must be n points starting from x0, it is x0, x1, x2, etc. at at xn minus 1. So, there are n points at which the polynomial interpolates this function. Then there exists, so I am going to now use the previous result. So, if P is a polynomial of degree at most n that interpolates a function at n plus 1 points, then at any t which is different from xi which I have used, f of t minus p of t can be expressed this way. So, now I am considering and denoting the polynomial that interpolates the function at a set of n points is a polynomial of degree n minus 1. So, using the previous problem, I know that there exists a psi belonging to the interval a b such that f at xn minus p at xn is 1 by n factorial into nth derivative at psi into product j is equal to 0 to n minus 1 xn minus xj. So, this xn is not one of the points in this list. So, here t is not one of the points in that list. Recall the error in interpolation that we already have determined. There also we had the point denoted by x, which is not any of the nodal points at which the polynomial interpolates the function. So, I choose the point xn which is not any of these points and use the error in interpolation formula which we had computed earlier and write down the result for the error at the point xn, which is this. Now, at this stage I use the previous result. I know by the previous result that f of xn, now xn plays the role of t in this problem. So, f of xn minus p of xn will be equal to f of x0, x1 etc. up to xn into product j is equal to 0 to n minus 1 into xn minus xj. So, the error in interpolation formula which we have already done gives me the error at xn to be this. The previous problem tells me the error in interpolation in terms of the divided differences of order n as this. The left hand sides are the same, they give you the error at the point xn, and therefore comparing the two results we show that f of x0, x1 etc. xn, the nth order divided difference is 1 by n factorial into nth derivative of at psi, and that is what we are asked to show. So, let us work out the following. A function is known at say 3 distinct points. So, let us call these points as x0, x1, x2. In the vicinity of an extreme point x0 of a function f of x, say of a function f of x, show that x0 can be approximated by x1 plus 2 x2 plus x3 by 4 minus f of x1 x2 plus f of x2 x3 divided by 4 times f of x1 x2 x3. So, if you know information about a function say at a set of 3 distinct points which lie in a neighborhood of an extreme point x naught of that function, then you can approximately get the extreme point x naught by computing the right hand side. So, what does it say? You have information at x1, x2, x3 about this function. So, the corresponding values are f of x1, f of x2, f of x3. Since the result involves divided differences, we immediately form the divided difference table. So, if I find the difference between the two, that will be f of x1 comma x2, which will be f of x2 minus f of x1 by x2 minus x1, and this will give me f of x3 x2. This is a 0th order difference, 0th order divided difference, and this will be the first order divided difference. So, I can form the second order divided difference, which will be f of x1, x2, x3, and the higher order divided differences will all be 0. So, now that you have the divided difference table, you can find the interpolating polynomial that interpolates this function at a set of these discrete points. Namely, f of x can be approximated by a polynomial p2 of x of degree 2. And in terms of the divided difference interpolation polynomial, this will be f at x1 plus f of x1 x2 multiplied by x minus the first point, which is x1, plus f of x1 x2 x3 multiplied by the factor x minus x1 into x minus x2. That is the interpolating polynomial. Now, f dash of x is 0. So, that will give you f of x1 x2 into derivative plus f of x1 x2 x3 into derivative of this, that will give you 2x minus x1 plus x2, and that must be equal to 0. 2x minus x1 plus x2 will be equal to minus f of x1 x2 divided by f of x1 x2 x3, and therefore x is equal to half of x1 plus x2 minus half of f of x1 x2 by f of x1 x2 x3. But when we look at the result, it also involves information at x3. So, I write down the interpolating polynomial again by looking at the set of values x2, x3, x1 and taking information along this diagonal. So, my interpolating polynomial that interpolates the function f of x can also be written as f at x3 plus f of x3 x2 multiplied by, so what should be the factor there? When it is f of x1 x2, it comes out to be x minus x1. So, here f of x3 x2, so the factor must be x minus x3. Then the next term will be f of x3 x2 x1, isn't it? Which is the same as f of x1 x2 x3. We have already seen the divided differences is symmetric in its argument. So, what will be the factors there? That will be x minus x3 into x minus x2. So, let us find out. F prime x is equal to 0 gives you 0 equal to f of, I can write x3, x2 as x2, x3, then plus f of x1, x2, x3 into again 2x minus x2 plus x3, from which we can get x to be equal to half of x2 plus x3 minus half of f of x2, x3 divided by f of x1, x2, x3. So, f prime x is 0 when x is equal to this. So, at an extreme point, which I denote by x naught, we have x naught to be given by this as well as this. Both are approximations to the extreme point x naught. So, if I call this as say result 1 and this as result 2, I use both these results 1 and 2, and that will give me 2 times x naught to be equal to half of x1 plus 2x2 plus x3 minus half of f of x1, x2 plus f of x2, x3 divided by f of x1, x2, x3. And therefore, x naught will be given by, of course, this is an approximation. So, I shall denote it as this. So, x naught is approximately 1/4 x1 plus 2x2 plus x3 minus 1/4 f of x1, x2 plus f of x2, x3 divided by f of x1, x2, x3. So, and that is what we have to show, that if a function is known at the 3 distinct points in the vicinity of an extreme point x naught, then x naught can be approximated by the value on the right hand side, and that is what we have shown. Let us now see how we can solve the following problem. It says the equation x cubed minus 15x plus 4 equal to 0 has a root close to say 0.3, and you are asked to obtain this root with 4 decimal place accuracy. We are given that this equation has a root close to 0.3. Suppose say I get the information about this function x, which is x cubed minus 15x plus 4 at some points in a neighborhood of 0.3, say at 0.2 and 0.4. Compute what is f of x by substituting x as 0.2 and x as 0.4. These 2 points are close to 0.3 and each is at a distance of 0.1 unit from 0.3. So, I can write down what is the value of f of x, which is 0.2 cube minus 15 into 0.2 plus 4. This is 0.4 cube minus 15 into 0.4 plus 4. So, since it is said that it is close to 0.3, I would like to find out the values at 0.2 and 0.4, and since it is a root at which the function must vanish, it has to change its sign either from a positive value to a negative value or from a negative value to a positive value, so that it will cross the point x is equal to 0 on the x axis. So, I would like to look at the value of the function at 0.2. So, this gives you 0.008 minus 3 plus 4, which is 1.008, which is positive. Then if I compute the value at 0.4, maybe since it is said that it is close to 0.3, I can even take this to be 0.3 and try. So, 15 into 0.3 plus 4, and the values will be 0.027 minus 4.5 plus 4, and it turns out to be minus 0.473, which is negative. Fine. So, I have at x is equal to 0.2, f of x is positive, and x is equal to, say, x is equal to 0.2, f of x is positive, and x is equal to 0.3, f of x is negative. So, it has to cross the x axis at some point between 0.2 and 0.3, and it is this point which I call as P, which I seek, which will give me f at P to be equal to 0, and that x is equal to P will be a root of that equation. So, what is it that I require now? What is the x which I call as P, such that at this P f of x is equal to 0? That is what is asked. So, I observe that I can compute this point P by taking the interpolating polynomial on these two nodes, if I call them as y0 and y1. So, I have the information about the y, which is f of x, at y0, y1, which are given at x0, x1. So, there is a y, namely 0, at which I do not have the information about the x, which I call as P. So, if I do the interpolating polynomial on the nodes y0, y1 and find out that x at which y becomes 0, then I will have the answer to this problem. So, when I do the interpolation on the nodes y0, y1, I essentially do what is known as inverse interpolation. So, when I take these 2 points y0, y1, I will be getting a polynomial of degree at most 1, a linear inverse interpolation polynomial. Once I get the polynomial, then I will get the information about the x at which this y becomes 0, and that would solve the problem. So, I need to understand the ideas in inverse interpolation, and we shall continue this in the next class.